Good morning. In this lecture, we will discuss something related to simulation method. So I have already distributed the lecture notes, so that will help you to understand this lecture. So basically, if you see any model that can be categorized into two kind of models that we have already discussed in previous classes also. We can have one kind of model that is called a stochastic model, another kind of model that we call is a deterministic model. So let's say try to understand what this deterministic model is. So a deterministic model is a model that gives same exact result for a particular set of input no matter how many times you recalculate the output using this model. So till now, whatever the model you have seen in previous classes or elementary classes, you have all models are deterministic model. For example, to illustrate this, let us take a simple example of calculating compound interest. So we use this kind of formula to calculate interest using the for a compound interest kind of thing. So let's say if I have a problem something like this, so determine the return on a 5-year investment with an annual interest rate of 7%. So annual interest rate is given, and for a 5-year you have to calculate what will be the final amount, and let's say P is the principal amount that is given, rate that is also given, and this is monthly compounded. So we have been given how many years we want to find the final amount. So we can use this formula and then we can calculate what is the final amount given the principal amount, interest rate, year, and the monthly you are compounding the interests. So we can use this model. Now if you see this model, this is the, I can use a Excel sheet to calculate this. So this is the principal amount, annual rate, and then finally we can calculate this future value, what is the final amount that we will have. So this is a deterministic model. So no, it doesn't matter how many times you can take any p-value or calculate for a given set of these parameters, you will always come across the same final amount of value. Also, for any other values you will get only final answer, only one final answer. So this kind of model that is called deterministic model, everything is deterministic, there is no uncertainty in this kind of model. So this is an example of deterministic model. So we can make predictions and what if studies using this kind of model or this equation. So now if I have this model, we can do some kind of what if studies. For example, what will the final final future value if I have a different annual rate and different m value. So depending upon that, so I can change this variable and I can calculate what will the future value. So to conclude, so in this kind of model, what we have a model, we have inputs, this can be a multiple inputs, and then we can have a multiple outputs also. If you see in all this, what we have x1, x2, x3 are deterministic, and the output y1, y2 are also deterministic. So this is an example of deterministic model. So in this case we have a deterministic model with x1, x2, x3 as input and y1, y2 as the output. Now next come to the stochastic model. So what we have in deterministic model, if I make input as a random variable, then my model becomes a stochastic model. So let's try to see this. A stochastic model is the one that involves probability or randomness. So my input is random, so my input is a random variable and output is also a random variable. So this kind of model is called a stochastic model. Basically a deterministic model can be converted into a stochastic model by making input as a random variable. So once you make the input as a random variable, your output also becomes a random variable. So let us try to illustrate a stochastic model using an example. So let's say find out the total profit of any company, automobile company. So let's say we can use this formula, total profit is equals to whatever the total income we have minus total expenses that we have for that company. So we can calculate using this formula what is the total profit. Now let us say if I have L this quantity denotes number of units sold per month, that is number of car or number of automobiles sold that month or for a particular time period. And then P is the profit per unit sale and R is the conversion rate. This can be because maybe it involves country to country, so you are buying from another country, you are selling in another country, so it requires some kinds of exchange rate. So let's say R denotes the exchange rate or conversion rate. So we can calculate total income, that is the number of profit per unit sale, times L, that is the total profit, and then we have to convert this into our currency, so we have to multiply by R also. So L times R times P, that will give me the total income. So income basically for 1 unit, and then this L is the number of unit, R is the profit per unit, and R is the conversion rate, and P is the profit per unit. So if we multiply these three, we can get the total income. Note that L, P, R all are random variable. For example, number of units sold per month, this can be a random variable. We don't know exactly how many units will be sold a given month. So if we are predicting something, and how much profit we are making per unit, because every unit, so every wire will have a bargain capacity, so every unit will be sold at a different price. So you see there is a basically randomness in profit. Also exchange rates also keeps fluctuating, so conversion rate is also a random variable. So my income becomes a random variable. Similarly, my expenses can also be a random variable. For example, expenses can be a combination of fixed overhead plus total cost of all the sales. So basically we can calculate expenses of a automobile industry by total overhead plus total cost. So let's say this is a fixed capital amount H, that is the total overhead, plus this is the total cost. So C denotes the cost of each unit, and L is the number of units. So we can calculate C times L, that will give me the total cost, and we have to also add the overhead. So the total expenses is H plus C times L. Once again, now C, L and H can be a stochastic quantity or a random quantity. So my expenses becomes a random variable. So expenses becomes a random variable. So now you see my expenses and profit both are random variable. So if we use this model, that is profit is equals to this term income that we calculated earlier, and this is the expenses that we also calculated. So my profit, that is expenses minus income minus expenses, is basically a random quantity or a stochastic model. So if you see in this problem we have x1, x2, x3, x4 correspondingly L, C, R and P as the input, and these input can be basically a random variable, and the final profit Y, that is the output of this model, will again be a random variable. So this is an example of a stochastic model. So this random variable can be described by any distribution. So now L can be uniformly distributed, normally distributed or exponentially distributed. So for each we can have either same random variable or same kind of distribution, or for each one we can have a different kind of distribution depending upon the situation. So to summarize, sometimes probabilistic models are so complex that tools of mathematical analysis are not sufficient to answer all the relevant questions about them. So this model is a relatively simple model, and we cannot find a we can do this kind of exact analysis using this distribution, but sometimes it becomes very difficult to perform a mathematical analysis. In those cases we can answer the relevant questions using simulation techniques. And so what we will do is we will simulate these inputs, and then correspondingly output will also be simulated, and then we can give the inference of the result, like what is the mean, what is the standard deviation, what is the percentage 95 percentile, all this kind of thing we can give if we once simulate the input value and correspondingly out value from this model. Now, once we do simulation, for all kind of simulation, we need a random sampling. So we need a random number generator. So let's come to this and let us discuss a little bit more about random sampling. So to illustrate this, any kind of simulation, so this figure basically illustrates how we simulate. So let's say we have a bag and that contains a large number of balls, and there are various colors of balls we have. So we can pick one ball at a time, and so let's say this bag contains infinite number of balls, so we can pick one ball at a time. So this is a random ball, and this does not depends upon other balls, or it does not depends upon how we are choosing. So this kind of sampling is called a random sampling. So basically we are simulating. So this is the basic idea of any kind of simulation. So we have to basically choose a number from a group of numbers, and this number should not be influenced by the other number. So my trial should be independent, and this should come from the distribution from which I am trying to get this number. So this is the idea of any kind of random sampling. So we'll come to this and we'll discuss in details about the random sampling. So basically, simulation means a method of selecting values from underlying probability distribution that satisfy the following requirements. So as we were saying, simulations means we have to choose a random number from a given probability distribution, and this has to satisfy two requirements. And what requirements we have? Each value of random variable in the sample space must have an equal likelihood of being selected. That's why this is a random sampling. So we have to select, so there is no biasness. We can select this number and that number with equal probability, or there is equal likelihood of being selected of all the numbers. So this is the basically criteria for a random sampling. Otherwise it will not be random. So if I associate some certain probability with some numbers, some other associate other probability with other number, this is a not example of random sampling. In case of random sampling, all numbers will have equal likelihood to be selected. The second criteria is each selection or trial must be independent of the previous trial, and that we were saying earlier, that is, if I have selected one, the next is independent. So all trials are independent, so there is no correlation in selecting the numbers, so they are independent. So two criteria, first is equal likelihood and the second is independence. Now the question is how we simulate this kind of numbers using computers. So basically computer provides an algorithms, and that can be used to generate these kinds of random numbers. So computer algorithms have been developed to meet these requirements. So we have two requirements. To meet these requirements, computer algorithms have been developed in somewhat artificial manner. This means the computer algorithm basically does not generate the accurate, or you can say exact, or you can say precise random numbers, because they are underlying some kind of algorithm, and that numbers are coming from that algorithm. So this means these numbers are not a pure random numbers. So any random number that is generated by the computer algorithm will follow some kinds of model, will follow some kinds of algorithm. So the number that is generated from computer algorithms are called pseudo random numbers, because they are not pure random numbers. We can try to increase the interval between two random numbers so that chance of getting the same random number becomes smaller and smaller and smaller. So basically only one thing we can do, we can try to reach towards the perfection, but we can never reach to the perfection, because these numbers are coming from a underlying distribution or underlying algorithm, and that's why these are called pseudo random numbers. So basically computers has algorithms, and we can artificially generate pseudo random numbers. So there are many algorithms. We'll discuss one algorithms, random number generation. So the foundation of simulation is the generation of a random number between 0 and 1. So if we want to generate a random number, what we do is we generate a random number between 0 and 1, and correspondingly we can generate another random number between any interval. So the idea is, basically fundamental idea is to generate a random number between 0 and 1. So what we are saying is, we want to generate a random number that lies between 0 and 1. So we already said computer algorithms have been developed to generate pseudo random numbers, because they are not exact random numbers, a very very long sequence of number that appears random, that is called pseudo random numbers. And in Excel we have a rand function that can generate the pseudo random numbers. What this means, this long sequence we'll discuss after some time, so don't worry about this. What is the very very long sequence? We'll illustrate this using an example. So when we are generating or when we are simulating random numbers, we require some initial value, and this value is called seed value. So a seed value is required or used to access a certain point in the long sequence, typically based on the computer clock time. So once we start to run my algorithm, or once we start to basically generate random numbers, we have to start somewhere, and this seed or a starting point is called seed value, and that is often taken from the computer clock time. So based upon the computer clock time, seed values are taken, and then random number generation starts. So one of the algorithm is called linear congruential generator. So this algorithm is often used to generate the pseudo random numbers. So let us discuss this algorithm. So this algorithm is used for a uniform random variable between a and b. So if we want to generate a random variable between a and b, so this is the algorithm. So this is a times xk plus b mod of m, and this will give me the next number, that is xk plus 1. So let's try to understand all this. So what we have, at certain point of time we have generated a random number xk, and then we want to generate another random number xk plus 1, that is k plus 1th iteration. So what we will do is, we will use this formula, and this will give me a number between a and b. So my xk is between a and b, and my xk plus 1 is also between a and b. And this formula says a times xk plus b mod of m. So what this means, this is saying I have a number axk plus b, and then divide by m, then whatever the remainder that is coming, that is my xk plus 1. So let us try to understand once again. So what we are saying, we have a number xk, multiply by a, add b, and then divide by m, whatever the remainder that is coming, that is my next iteration number, that is xk plus 1. Now so this xk plus 1 is between a and b. If we want to convert this random number between 0 and 1, then we have to divide by m. So if I have a random number xk plus 1 divided by m, so that will give me a uniform random number between 0 and 1. Let's call this random number as uk plus 1. So uk plus 1 is equals to xk plus 1 divided by m. So we will illustrate using an example, and this algorithm is called linear congruential generator. So let's say we take a value of a equals to 11. So in this case a equals to 11, b equals to 7. So we can take basically any values for a, b and m, and m equals to 17, and let's start a seed value. Seed value means initial random number, that is x0. So we can start with x0 or initial seed value of 4, and then we can use this to calculate the other random numbers. So the sequence repeat itself by m trials. So now you see m is the number, that is 17. So we'll see soon that the sequence of random number generated by this algorithm will repeat itself after the m trials. We'll see this soon. So parameters of random number generators are chosen such that the cycle length is extremely large. So this means if I don't want to repeat my numbers, my m value should be very high or very large, that is the cycle length m. So we want to my cycle length is very extremely large, so that we don't want to repeat my random numbers. So random number is a sequence of so this random number, that is basically will be, if I take my sequence very large, then that case these numbers will also be uncorrelated. Also I have to choose this parameter such that these two numbers, basically any consecutive two numbers, should not be correlated. So we have to, basically what we are saying is, we have to choose a, b and m in such a way that basically satisfy the random number generation assumption. That is, the first assumption is these numbers should be independent and uncorrelated. So basically we can take this initial starting value or a, b and m value, so that these basically satisfy the assumptions of a random number. So let's say using this, whatever we have a, b and m, using this b simulated random number, and these are the random numbers. So we have a trial 1, 2, 3, 4. So correspondingly we simulated the uniform random number between 0 and 17, and we simulated uniform random number between 0 and 1. So we will illustrate this using an basically Excel sheet, so that you can understand whatever we are saying here. So let's say go to this Excel sheet, that is the random number generation. So if you remember, we have this xk plus 1 equals to axk plus b mod m, and this uk plus 1. So there are two sequence that we have. So let's say a, b, m value. So let's say a equals to 11 and b equals to, so we have to start somewhere, b equals to 7 and m is equals to 70. So these are the value we know. And let's say seed value, that is xk, that is the starting value x0, or let's say first trial, this value is 4. So these are the value that we have basically set here. So this value we have set, and then we can generate the random number. So this random number, so let's say we can remember this. Let me copy this, and I can also put it here. Now let's start. So basically I have already done, so we will do this again. So let's say we have a trial. So first trial, second trial, third trial. So we can many number of trials, and then we can generate a uniform random number between a and b, that is a is 11 in this case and b is 17. So we'll generate uniform random variable between a and b. So this is the uniform random variable. So let me so this is the uniform random. So what is algorithm? Axk plus b. So we have to write this is equals to a value is 11 times xk, and in this case xk is basically initial starting value 4 plus b value is 7, and then we have to divide by, so let's say this divide by m. So in Excel we have a function to getting the remainder. That function is called mod, and this function takes your number and divisor value, so that if you can see here, so number and the divisor value. So in this case divisor value is 17. So this will give you the value of the random variable. So in this case this value is coming out to be 0. Let's calculate in the next iteration. So again we have to calculate this. This is the mod, and then we have to put the number. A number is previous number divided by m is 17. So I have to basically make here a times what is a value. A is 11 times previous value plus b value is 7, and then this divided by 17. So this will give me the corresponding number. So this comes out to be 7. Now so what we can do now is we can basically extend this, and then we can get the random numbers. Basically the first random variable was 4, so the seed value was 4, so we don't have to basically do this formula, so we can simply put this is equals to 4. So this value was 4. Then we can get the random number. So you see what we are saying is we are basically using this step. So this step gives me the random numbers xk plus 1. So xk was 4, so initial value was 4, so the first iteration value is 4 here, and then the next iteration value will be a times xk plus b, so that this value we have a times xk plus b and divided by m, that is 17. So that will give me the next iteration value. So these are the random numbers we have here. Now we can calculate again uniform random number between 0 and 1. So we can calculate this. So what is the algorithm? That is xk plus 1 divided by m. So if I want to calculate the any value, so this is simply this value divided by m, and m in this case is 17. So this value is 0.24, and then we can basically calculate all these random numbers. So you see we have calculated uniformly distributed random numbers between 0 and 1 and between a and b. Now if you see we have these values. Now when these values start repeating, so if you see after 17th trial, this value is 4 and this value is also 4. So you see in this case this value is repeating. So 17th trial, this is 4, and the same uniform random number between 0 and 1 are also starting repeating. So this is 4, then 0 0, again you have 0 0, 7.41, again you have 7.41. So your random numbers are started to repeat. So this means if I keep my m last, in that case this chain length will become larger. So if I choose my m and correspondingly a and b in such a way so that this length increases, in that case we can basically try to reach towards the perfect random number, but of course we will never reach to the perfect random number because this is coming from an algorithm, and that's why we call this as a pseudo random numbers. So this is all about generation of a random numbers. Almost all computer algorithms have, or all computer programming languages have some function that uses to generate a random number between 0 and 1. For example, in Excel we have rand function. If you want to generate normally distributed, then we have rand function. Similarly, MATLAB other also have the random number generation function that can be used to generate a random number between 0 and 1, and correspondingly you also have the function that can be used to generate a random number from any particular distribution between 0 and 1 or any other values. If you give the mean and a standard deviation, it will give you a random number between a and b. There are the two intervals in which you can get the random number. So let's come here. So we have demonstrated how we can use to generate a random number algorithm. We can use an algorithm to generate a random number between a and b and 0 and 1. Now generating a random number bit from any distribution uses this fact whatever we have discussed just now. So basically we discussed that random number we can generate between 0 and 1, that is coming from a uniform distribution. And then we will use this fact that I know a number that is coming between 0 and 1. This is uniformly distributed, and then I can use this fact to generate a random number from any distribution. So what is the idea? Idea is to generate a random number from any particular distribution. This distribution can be normal, this distribution can be exponential. So any kind of distribution we have, we want to generate a random number that follows that distribution. And idea is very simple. So whatever we have discussed, so let's say I know a random number between 0 and 1. So this be simulated or be generated a computer algorithm. So we have a random number between 0 and 1, and so this is coming from uniform distribution. So on the y-axis we have corresponding PDF. Generally we plot on the x-axis number and the y-axis PDF. Here we have the axes are interchanged. On the x-axis we have PDF value. On the y-axis we have basically numbers. So we have the random number that can take any value between 0 and 1, and the corresponding probability in each case is same. So if I want to 0.24, this has the same probability. 0.8, it has also the same probability. This means this is coming from a uniform distribution. So once I have a random number, so what we are saying is we have generated a random number, so let's say UI, from the computer algorithm that we just discussed. Now we know the fact that any CDF value, so CDF of any function lies between 0 and 1. So my random number UI also lies between 0 and 1, so that we said earlier. So now we will use this fact to generate a random number from any distribution. So what we do is, so let's say we plot CDF of a distribution. So this shows the CDF of a distribution. So this is something of this distribution. And then for this distribution, this is the CDF. So I have here PDF of any distribution. So on the x-axis we have the corresponding x values, and the y-axis we have the corresponding density values. So we have this PDF value here, and this is a CDF function we have in this case. So what we are saying is we will use this idea that CDF lies between 0 and 1, and my random number also lies between 0 and 1. So we can calculate, or we can estimate, or we can generate a random number using this idea. So what we are doing is illustrated here. So let's say we have a random number UI, and then corresponding random number, I go to the CDF, and corresponding CDF I see which value corresponds to this UI. And once I know this UI and this value, then we go to this on the x-axis in the CDF, then we calculate this xi and the corresponding xi value that is coming from the distribution. So once we know a random number, we go to the CDF for a particular distribution and corresponding CDF value from which distribution, for what value, this will give me the corresponding CDF value. So this is the idea of generating a random number, and this technique is called inverse distribution method or inverse CDF method of generating a random number. We'll discuss in detail of this method of generating a random number. So basically this has 3 steps. So in the first step, you have to simulate a random variable UI using the Excels or whatever you have a computer program. So using that, you generate a random number UI, and then equate this UI to the CDF of that corresponding distribution. And then once you equate this, you can invert this function to get the xi value. So basically you have to take an inversion, solve xi by inverting this function, CDF function, f inverse of ui, that will give you xi value. So if you have a analytical formula for fx, if you remember, in some distribution we derived what is the expression for CDF. In some cases we are not able to derive, and that in those cases we have the tables. In some cases we have basically derived the expression for the CDF. Once I know the CDF expression, I can invert this function and correspondingly xi value can be obtained. So basically the assumption behind this inverse CDF method is that the random number drawn from the uniform distribution corresponds to a probability distribution between 0 and probability between 0 and 1. So therefore the CDF of a random variable is equated with the random number from the uniform distribution between 0 and 1. So this we already said. Basically we have a random number between 0 and 1, CDF lies between 0 and 1. So we can use this idea to equate the CDF, and in the next step we can basically invert this once we know the analytical function for the CDF to calculate or to estimate the value of xi. So solving it of xi is a straightforward for some distribution, and readily available expression for f inverse x can be basically derived, or it can be seen in any textbook. For example, in case of exponential distribution, you can basically derive an expression for f inverse x. In another cases, in those cases you don't have basically this kind of inversion available. In those cases you can go to the table and see the particular value, and then go to the value for which value of x this corresponding CDF value corresponds. So this can be basically done using the computer program, and almost all computer languages has a function that gives you for a given value, it gives you the inverse value. For example, in Excel we have NOR inverse function that will give you for a given random number ui what will the corresponding xi value. So use this, and we can also have the same kind of function in MATLAB and other languages also. So to summarize, in this lecture basically what we said there are two kinds of model that we have. One is called deterministic model, another is called a stochastic model. In cases where you have a input that becomes random variable, your output also becomes a random variable. Those kinds of models are a stochastic model. In some cases, getting result or getting inference from the stochastic model is mathematically expensive or even not easy. In those cases we use simulation technique. So in simulation what we do is we take all these input variable that is coming from some distribution, and then we put this distribution into the model, and that gives me the output value. Now for simulation what we have is we have to simulate a random number, and to simulate a random number we have the algorithm, and there are many algorithms available in the computer. One algorithm is linear congruential random number generator. That is a linear, you see this is a linear, so you see this function that we discussed earlier was linear. So this gives you a random number between a and b, and then divide by corresponding m, then you get a random number between 0 and 1. Once you have a random number between 0 and 1, this you can consider as a CDF value coming from any distribution. This means once you know the CDF value, then you can calculate corresponding xi value for a given particular distribution, and this method is called inverse CDF method. So once you have this xi value, you can basically perform simulation tasks. So all this simulations are very powerful in those cases where we don't have any mathematical models. So in those cases we can perform simulation to get the results. So we stop here. In the next class we'll discuss little bit more about Monte Carlo simulation. That is another example of a simulation. So we can stop here. Okay, thank you.